Good afternoon, everyone. Okay. Boom. Okay. There we go. Okay. Last time we looked at did we look at? Matter, right? We were looking at matter. That's right. We were trying to do a classification thing, and we were looking at this. And we finished this sheet just so that you Karen, so that you know that's what we did. We finished this sheet right here. It's called matter packet, but we're done with it. So let's go back. Okay, so the next thing to do is really not much. It's just the phase changes diagram and the connect. This is the main thing, the kinetic molecular theory. When you're looking at, remember, theory is not just a thought. It's in chemistry or in any science or theory. It's something that's been done a lot and by different scientists, different angles, different everything. Oops, that is not the one. Nope, go away. Okay, this is the one I want to open that one. All right, so when you're looking at it, basically, there are some things that you need to know, and that's what this diagram is supposed to do. And I don't know where it went. That is not it either. Okay, come on, you. Why did you not want to open? There it goes. Okay. I'm not going to edit it, but I enable editing so that it makes it bigger. Okay. So the four things that are most important is how the intermolecular forces are acting, the temperature, the kinetic energy, and the distance between those molecules. So you know that in a gas, right, everything here is going to be at the max.
I'm not showing your screen.
You cannot see my screen. I shared
You're
it.
not sharing it.
Okay, hold on. I shared it. I guess it didn't share. All right, let me share it again. Come on, share. See, it's not. There it goes. Okay, that's probably what happened. I just hit share and assumed it made it. Okay, so you can see that, right?
Yes, I can see it now.
Thank you for letting me know. Okay, so like I was saying, in the kinetic molecular theory, what matters are these things. And the way that I drew this, or kind of made it, I didn't draw it, but I made it, was by showing you that the forces go from low to high on the diagram below, right? And from low to high to the left, from the left to the right, and the right to the left on this one. But the three things that are always going to be increasing as you go from a solid to a liquid to a gas are going to be the temperature, the kinetic energy, and the distance between them. But the intermolecular forces are the only thing that goes the other way. Because it makes sense that you'd be more attracted to something, so you stay closer, right? Which is exactly what's going on here. Because a liquid, let me make it smaller, a liquid has less intermolecular forces, and a gas, they were pretty much gone. So when you look, and what is intermolecular forces? Those are the forces of attraction between the molecules. And we'll look at those later in more detail in a different unit, but this is matter right now. So we're just talking about them. We're not really knowing anything more than that. But basically, like I said, the forces of attraction between molecules or atoms or whatever it is in a substance. Okay. So as we already know, when we go from a solid to a liquid, we call that melting, right? That's on top, you see that? And from a liquid to a gas, that's evaporation. Well, then we're going from a gas to a liquid, that's condensation, and liquid to solid, that's freezing. But did you know the other names? When you're going directly from a solid to a gas, it's called sublimation. And from gas to a solid, it's called deposition. Sublimation, you've seen it probably quite a few times if you've seen dry ice. You notice how the dry ice is a solid and it smokes, like people call it smoking, but it's really just evaporation of the dry ice. And you've also seen deposition, you just didn't realize it. When you wake up in the morning, in a cold, cold morning, and there is dew that has been frozen so on the ground, right? That is deposition because it goes directly from vapor to the frost that is on the ground. So that's deposition. All right. So this is what this diagram is doing. Pretty much it's telling you all about the intermolecular forces. Now, the diagrams that we're going to see after this one, we're going to look at, and they're going to go from, it's called the phase changes of water. And sorry, I'm going to go back to it and we'll get to it here in a minute. All right, here we go. So when we're looking at this, we have the phase changes, see that? And this phase change diagram of water is going to go through some words that you're probably not familiar with. Some of them you are, of course, but some of them you're not. Okay. Here we go. This is a little blurry. If I make it too much bigger, it's going to be even blurrier. But basically, it says phase change diagram for water, and you have temperature versus heat. So you would not expect temperature versus heat because everybody thinks they're one and the same. That's why I had you look it up, remember? All right, so boiling point of water, and this is in Kelvin, by the way, because that's what metric is. Boiling point of water is 100 Celsius or 373 Kelvin. And this plateau right here, that is the boiling point. Why is it a constant? Because the molecules that are coming from here are transferring energy to get them up here. So this remains constant until the last molecule has turned to steam. Same thing here. This is the freezing point or melting point, either way, depending on which way you're coming, of water, which is at 0, right? Celsius or 273 Kelvin. Now you notice there's an HV and an HF, and the HV is much longer than the HF. That's because the HV is the heat of vaporization, and if you notice, is 540 calories per gram of water, whereas the heat of fusion, which is around the melting point, is the heat, the amount of heat that it takes to change. So basically, that's what it is. And it's only 80 kilocalories. So it's a lot less. So that's why it's less length. You know, the line is shorter. Okay. So when you're boiling water, you're going to have a rapid increase, right, of the ice that's going to be changing to water, to liquid. And then you're going to have a plateau. And until that last molecule has gone from a solid to a liquid, this will not be released. Then it'll release and it'll come up. And this is much longer, as you notice, because it takes a lot more heat. Well, think about it. Here, we're just changing to a liquid. That's the intermolecular forces are still present. You know, the molecules are still kind of close. So you're not having to do much here. But from a liquid to a gas, that's a big difference. So you got to do a lot of absorbing of energy, a lot of increasing, right? And then finally, you hit the plateau, and that takes a long time also, because you've got to break all those intermolecular forces. You got to weaken them here. You got to, you got to completely get rid of them pretty much to turn to steam. So it takes a lot of time. So if you notice also that the slope are different, right? The slope of the solid to liquid is very steep, so that means it happens quickly. The next one is a little less steep, and the last one is it's a lot more, how would I say, not so steep, less steep, whatever. Yeah, the least of all. And that's because you're already in steam. So this is how it works. This is your entire heating curve of water. We used to do this in the lab with ice, and they would record the temperature every minute. I know it's annoying because it takes a long time. Every minute, and that way you wouldn't miss the heat of vaporization or the heat of fusion. They would record it versus time. So this is a little different than this diagram, and I'm going to show you the difference of that. We used to do this same experiment though, but the diagram does not look the same. Well, it looks the same. It's just the X and Y are different. And that is the next diagram. The phase changes, where are you? Chart, I guess this is it. Yeah, this is it. Okay, so when you look at it, I'm gonna make it bigger, of course. You can see this one is actually explaining more to you than the other one was. So here, it's all about the phase changes. That's all it is. Has nothing to do with, with how much heat of vaporization, heat of fusion, none of that. But this one is just telling you that when you go from see the slopes and the condensation point, freezing point, melting point, all of those, they look the same. Well, it's not so, but the solid is, as you can see, reaching the temperature. And obviously that right there should be 0, right? Because it's Celsius. And the boiling point right here would be 100. So they made it really short. But I like this one because it actually shows you how you're adding heat. When you have a closed system that you're heating up, the heat comes from the environment. And that's something that you'll learn if you take Chem 2. We'll be looking at that. And that kind of can get a little confusing if you're not thinking straight. So you're coming in from the environment, right? So if you're absorbing heat, the heat is being taken from not the system. Whatever is not the system is the environment, and put into it. And so it's absorbing. Whereas when you're melting or condensing, right? I'm sorry, freezing or condensing, then you're going the opposite. You are removing the heat, and you're removing the heat and giving it back to the environment. And that is what is the cooling phase, right? So you got to cool down to come from a gas to a liquid, cool down some more to get to a solid. So you got to remove that heat. And that's one of the things that you have to remember. So a lot of the times people don't realize, but whenever it rains, you know how it gets really muggy at first before it rains? And that's because you are actually getting this to happen right here. You are evaporating a lot. So you're having all these molecules in there. And then when you finally, so you're removing heat, yes, but the heat is still in the environment. And I mean in the system, and the system in this case happens to be the atmosphere, right? So that gets warm. But then when it rains, it cools down because you've already dropped the temperatures so that you can get cooler. And the other thing, it also, the cycle has started back again. So it's just a cycle that goes from evaporation to condensation, and then of course precipitation. But anyway, so that's how that works. Escape, let me go back. Okay, this is not, okay. So that was the last part of this. And the other thing is to one more time get to look at our phase changes. Let's see. Oh, no, that's not it, sorry. How to separate the mixtures, yes. Because that's one of the things. There is a matter point. Okay, so there's a matter is. This one is the one, I think this is the one that I like right now. I have to check because I give you 3 different PowerPoints, but yeah, this is the one. Okay, this one goes over some of the things that we want to look at, which is some of the properties of metals and nonmetals, which we want to look at too. Open this one, close that. This is gibberish. Okay. Yes. Okay. So here we go. So for this one, we're going to kind of like a quick review of everything we've learned too. So as you know, chemistry is the change, the study of the composition, structure, properties, and the changes that matter undergoes, all of those things. For example, right here, this what you're seeing is this equation, which is ethyl alcohol burning in oxygen to produce carbon dioxide and water, plus of course energy, which you can see here as the fire, right? So you have reactants being changed into products. So there's a change. That's a chemical change. And that's weird. Okay, so matter is anything that has mass and takes up space. And mass is a measure of the amount of matter, right? An atom is the smallest unit of an element. An element is a pure substance made of only one kind of atom. And there's your periodic table. A compound is a substance that is made from the atoms of 2 or more elements that are chemically bonded. For example, sucrose, sugar. And then you have extensive properties, which I was telling you that depend on the amount of matter that is present. So like mass, volume, anything that the more of it you have, the more of this property you have. In intensive, they don't depend, like melting point, boiling point, any of those, because, or density even, because your ratio of mass to volume remains the same. And that is why it's known as a property. Here's some examples. And here are some examples of intensive properties. Okay, a physical change It's a change that that the substance undergoes, but it does not involve any kind of change in its identity. So like I was saying, if you have ice and you leave it out, you just get water. And ice, all it is frozen water. Same thing if you're boiling it. If you're boiling water, you're getting steam. All steam is water is the gas, right? All right, so here's the different states of matter. And this is something we need to look at. Remember, we're adding heat as we're going towards the right on this diagram. Solid. Okay, a solid has definite volume and definite shape. The particles are packed and they're in fixed positions so that all they can do is really vibrate. Another thing that's a difference here is that a solid has an upper surface, right? You can put something on a solid. Liquid has a definite volume, but an indefinite shape. The particles are close together, but they're not in fixed positions. That's why they can change shapes. Also has an upper surface, because you know how you can float anything on water. That means there's a surface. And you have a difference between the water and the air too. So that's another one. Gas, though, has neither. Doesn't have a definite volume or a definite shape. It is compressible. That's another thing that you have to say about gas, that you can compress it into a smaller container. The same amount of gas, because you can remove some of the distances. And you can compress it enough, you make it into a liquid also, because pressure will do that. One of the things, it doesn't have an upper surface. Yes, things will float in it, but they'll keep on going up, right? So that's just because it's a gas and the other thing is lighter, that's all. So no, you cannot place anything on top of a gas. There is nothing that has an upper surface there. And plasma is just a high temperature gas, basically. And it is found in the sun or any other star. As you know, the sun is a star and they're made of plasma. So plasma is actually the most common form of matter in the universe, but not on Earth. Okay, so there's your particles in a solid, particles in a liquid, and particles in a gas. As you can see, they're very different. Okay, so here's copper. Look at the temperatures it takes for copper to be still a solid. I mean, it's quite a bit. Copper will stay a solid unless you go above 1,000 degrees, almost 1,100 degrees. This is a liquid. So once you've melted copper, it takes this amount of heat. Look at this, the temperature, I mean, to go into a, because it's a remember, heat is exchange, into this amount of temperature. This is ridiculous. We're going to almost 2,600. It's still a liquid at that. And then you can make it into a gas. Yes, you can vaporize copper, but it takes an ungodly amount of heat, as you can see. All right, so a chemical change is a change in which one or more substances are converted into different substances. For example, these fireworks. Heat and light are given off, and they are evidence of a chemical change. You can also think of bubbles, a smell that's changed, a color that's produced where there was no color to begin with, things like that. Consistency even, but I'm not talking about state of matter, but more like the milk. You know how the milk gets chunky? Yeah, like that. Okay, so here's a classification of matter that kind of like what I asked you guys to do, except I didn't want it this way because this is a flow just for you to figure out. Like I say, as I say, for example, carbon dioxide. So you say, can it be separated by physical means? The answer would be no. So it would be a pure substance. Can it be composed by ordinary chemicals? The answer is yes. And that would be a compound, you see? That's how you would classify it. Or let's say salt water. Separated by physical means? Yes. It's a mixture. Is the composition uniform? Yes. So you have a homogeneous mixture. And there it is. See? Okay. This is where it comes in. The separation of a mixture can be very tricky depending on what your mixture looks like. If it's just like Chex Mix, you can sit there and do it manually, right? No big deal. But what if you have all these weird little tiny things with different properties and all that? Well, you focus on the property that's going to help you separate it. For example, right here, the components of dyes, such as an ink, may be separated by paper chromatography. And depending on whether it's water soluble, like, your water soluble markers, you could use water. But if it's permanent marker, no, you need alcohol. Another way to separate it is using distillation. Oh, and in this case, I forgot to mention, in this case, everything is soluble in the same solvent. And a solvent is what you're putting things in, and the solute is what you're putting into the solvent. So for example, if you're making salt water, the water is the solvent, the salt is the solute. And of course, the salt water is the solution. Okay, so in this case, you want to separate a solution of something, and you want to actually keep the solute. In this case, you want to keep the solvent also. Okay, so when you want to keep the solvent, you want to do distillation. Distillation is all done by the differences in boiling points. Let's say you had a mixture of alcohol and water. You can't hope to separate it. So what you would have to do is you would have to boil it, because alcohol actually boils at a different temperature. As a matter of fact, in one of the labs, they have you do this, don't they? Where you're trying to increase the production of ethanol, remember? For the people of the little town. I don't know if you've gone to lab yet, but that's what you needed to do, was a distillation. Anyway, once you distill, you have a thermometer here, and you know your target. You know that, let's say, your ethanol will boil at, I think it's 80, or is it 78? I think it's 78. I can't remember. But the thing is, it'll boil, it'll evaporate, and then you want to stop it at that point, because otherwise you're going to get a mixture of both. In this case, you still get a mixture, but because water will start to evaporate anyway, but it's very, very small amount of water. And then you can do a second distillation until you're clear. So that's another way that, I don't know, I mean, I know you probably don't drink, so you're kind of young, but if you do, the things called distilled spirits, that's how they do to increase the alcohol content. They distill it. They still some of the liquids out of it and distill the alcohol so that they can add it back. All right, this is an evidence of a chemical change right here. Okay. This is the compounds must be separated by chemical.
Excuse me, Dr. Vibes. I mean,
Yes.
Miss Vibes. I have to leave class.
I saw your message.
Okay.
That's fine. You are fine. You can just watch the lecture later. Okay, so if you want to separate it by chemical means, right? Then you need to apply some sort of, I don't know, something that makes it separate. So in this case, it's electricity. I was going to say force, but it's not necessarily force. It could be just an agent. Let's just say an agent that separates them. And in this case, it is electricity. And you get this separation of hydrogen and oxygen. And that's what they're doing with the hydrogen power engine. They're trying to make it separate so that they can use hydrogen as fuel. All right, so here, remember we looked at these, and the most common ones are the alkaline metals, alkaline earth metals, the transition metals. I had told you about the boron group, carbon group, nicogens, chalcogens, halogens, and noble gases. And then the whole thing on the bottom, both of these rows are called the rare earth metals or inner transition metals. And the top column is called the lanthanides, and the bottom is the row is the actinides. Okay, so we looked at those already, but we're just going fast. All right, here's the properties. You might want to write these down. Properties of metals, well, you can kind of see them. They're shiny, right? They have luster. You know that they conduct heat very well because copper is used in wires, right, to conduct heat and electricity. Pots that are used for cooking, they conduct heat very well, but not too well that you burn, you know. Metals are malleable. Malleable meaning that they can be pounded into thin sheets. Think of gold foil or aluminum foil. Metals are also ductile. Think of wires. Ductile means that they can be drawn into thin wires. And very expensive components, audio components have gold wires, right? And silver wires, yeah, because they conduct so much better. They also have high tensile strength. What does that mean? It means it's hard to break it. Have you ever tried breaking metal? It's not easy, is it? And they also have luster, which means shine. And those are your properties. Examples of metals, you have this beautiful thing here called potassium. Potassium is very reactive with water, so you cannot just leave it out. If you do, you're going to have an explosion because the water in the atmosphere is going to react with it and make it have a very violent reaction. And a violent reaction in a short amount of time causes an explosion. So what they do is they store it in something that is not going to do that, like kerosene. They also have mineral oil and things like that that you can store it in, but they coat it. This right here is a bar of zinc. Zinc is very stable, very much more stable than potassium, so you can leave it out, no problem. That means it's less reactive. That you recognize it because of the color, right? That's copper. It's very soft and a very good electrical conductor. And you recognize this guy because he's the only liquid metal, and that is mercury. Okay, nonmetals, and they have this, for example, the graphite in pencil lead is not lead, it's actually carbon, and it is non-metallic. And they are, and you know this, now you can think about it, since you know that graphite is non-metal, carbon or charcoal, right? you know, they're poor conductors of heat and electricity. They are very brittle because look how often your pencil breaks, your lead breaks. I mean, there are many are gases at room temperature. We looked at that last time when we actually colored or made a little balloon or whatever people wanted to do to mark the ones that were there. Okay, example of nonmetals. Here's one. Do you recognize that? Anybody? Being yellow? No? Well, that is sulfur. Yes. Sulfur. Sulfur was, you know, when people call it brimstone, it's because of the smell that always gives out. That's a fire and brimstone, you know. Okay, so that's what that's about. And then this is a very reactive metal. Non-metal, sorry. Element, I was going to say. And this is a form of this element known as red phosphorus. And here's another one. Yes, that's a diamond. And diamonds are pure carbon. And do you remember that lead was also pure carbon? This is what is known as an allotrope. An allotrope is an arrangement of the atoms. The allotrope of diamond is very, very strong, whereas the allotrope of carbon, the lead, is very weak, because that's why it breaks so easily. Interesting how that it can be both. And the color, yeah, the color comes from impurities in according to the crystal structure. Okay. All right, metalloids. These are our metalloids. You might want to mark them in your periodic table. So yeah, I've always known as polonium and astatine as being metalloids, but in some books, they don't mark either polonium or astatine. I don't know. Or they don't put either one. I don't know why. This is when I studied, this is what they were. We had a total of 8, and that's what I always have known. But now they're trying to cut them down to 6. I don't know why. I haven't read about it. I think it varies because I've seen it in different books, different ways. So I don't know if there's a real reason. Okay, so they are the ones that straddle the border between metals and nonmetals in the periodic table. That line that has your periodic table that I gave you has, that's the line that they're talking about. They have properties of both metals and nonmetals, and some may have more properties of metals, some may have, you know, it just depends on who they are. Metalloids are brittle than metals, but more brittle than metals and less brittle than nonmetals. So they're in between in this case. And they are semiconductors of electricity, which means they will conduct, but not as well as a metal, and not as poorly as a nonmetal. And they possess metallic luster. Some of them do, not all of them. And here's an example of one. Look how pretty it is. That's silicon. Silicon's shiny, right? Metallic luster. It is brittle like a nonmetal. It is a semiconductor. It makes these little guys. Reason why we can actually hold class like this is because of this metal called silicon. I mean, metalloid called silicon. And here's the other ones that are more popular. And that's it. All right. So after you know that, that's the changing matter. Now, we are going to look at one more. Oops, sorry. That's not what I meant to do. We're going to look at one more thing here. And that is you notice that you have an essay question. And I had put the rubric. So let me bring up that rubric. I think I'm going to have to go get it elsewhere because I do not see it here. So I'm going to probably have to go to my sheets here and look for rubric. Yes, there it is. Okay, so the rubric is going to look like this. All right, and I'm gonna post it for you, but basically it just depends on which one you're doing, right? It may not have the sugar, the copper slag, the grass beads, but I think yours does. It might be different materials, but the point being is you get one property, 1 point if all the property, or one property at least is identified. You get 1 point if the materials are used to separate it, the proper materials, obviously. You get 1 point for the description of how to separate it. And if it is an incorrect process, you get 0, right? So the coppers, same thing. So basically you're getting 1 point per thing. And then there's a narrative that you have to write. All steps are included and defined. Left out 1 or 2 steps. Left out 3 or more, or they're wrong, 1 or 2, or then did not write a narrative. That is no points. So you can get up to 15 points by doing just a separation, and then 5 more if you do the narrative. The narrative is best because when you see what I'm talking about, the essay question, and it's not just 3 for you guys, it's just 2, but like I said, I have to adjust all of that. But the actual essay question that I usually do is I actually show you an old one that I've used before. Yeah, like this one. And we go over it. And I explain to you how I want you to do yours. And you'll be looking at also your rubric. So the way that this is going to work. Okay. This little table was given to you just for you to do a quick plan, right? Plan it out. Okay, so first of all, nickel, and we need to look for nickel on the internet. And if you look for it, you will see that it says that it is, let me see, where's my periodic table? One of what is known as the iron triad. The iron triad are all magnetic, and that is iron, copper, and nickel. I mean, cobalt, copper, not copper, cobalt and nickel. So I would use probably the glass beads first, because the glass beads are pretty big. And you got, look, if you read, it says sieves with 5mm holes. So this, see, I'm just gonna Control C. The material that I'm gonna use is I'm gonna use this one, right? Why am I gonna use that? Because I can retrieve it by putting it through the sieve, and the glass beads will stay there, but everything else is smaller than that, so it'll go down. So the property I used was size, wasn't it? Were there any additional steps? No. How do we separate? We call it filtration. Filtration you do when you want to separate things by size, or when you want to separate things that are not soluble in water, okay? All right, next one, I would do the copper. I mean the copper. I keep saying copper. My brain is going to the one you're doing. Okay, I would do this one. And I would use, look what's here. What did I just tell you? The nickel filings have magnets. There we go, because they are magnetic. So I would use this next. Okay, so I would use a magnet. And of course, how are we going to separate? Well, you can call it magnetic attraction, right? Because that is why you are separating it. And the properties is magnetism. Okay, No additional steps required there. What are we left with? Poppy seeds, copper slag. Oh, there's the copper slag again. And table sugar. Okay, so this was not meant to be the one. We're separating the one you guys are going to do. No, let's not do that one. I want the old one. I want to do a different one. That one said 2020, so I thought that would be the one, but let me see. I've been using it for a while, so okay. Let me see what this one looks like. Nope, this one's changed too. Okay, I have to find another one. I used to use a different one, and that's the one I need to find. Let's try this one. Let's see what's in this one. There we go. We have different ones. All right. So once again, we've got pretty much the same things. It's just the properties are going to be a little different. Okay, so in this one, you have iron filings. You still got the copper BBs, which are larger. So I would use them first. Copper are not magnetic. So how are we going to separate them? Once again, we said, well, you know, I'm doing it my way. You can do it your way. Like you can actually use a tweezer and grab them. That's fine. If that's what you want to do, do it. As long as it's effective and it doesn't take you half the year, you know. Okay, no. Sorry, that's in the wrong place. I'm going to put it here. Okay, how do we separate it? We call it filtration, remember? Okay, well, filtration, okay. Sorry, there we go. The properties was the size again. No additional steps. This one, see, it's pretty similar. You just got to identify which one's which. The iron filings was magnetic, so we're using magnets. Okay, so we're going to use material uses magnets. I'm going to call it magnetic attraction, right? And then the property is magnetism. Okay. Now you have styrofoam, pellets, sand, and salt. If you put water into this container, oh, and that would have been 2, by the way. Okay, so you're going to add water. That's your additional step because the density is going to help you here. The styrofoam is going to float. So one of the properties that you're going to use here is density, and you're using it on all 3 of these. Not for salt necessarily, sorry, on those 2. Here you're using solubility, right? Because you're soluble. And here too, because they're insoluble, you can say you're using solubility here too. Okay. All right, so how are we going to do this? We're going to add water. The styrofoam are going to float. And look what we have on our materials. We have these things called small fish nets, you know, like what you use to transfer the fish when you're changing the aquarium water, that. So we're going to use those. And that's going to be known as filtration again, right? Because you are taking it. Oops. There we go. That's what I did last time too. All right. So we're also going by size because they're insoluble, right? The size is going to help us here too. The density helped us for it to go up. The solubility made it not, not dissolve, which is good. And then the size helped us retrieve it with the fish nets. So all 3 of those were used. The sand, I would use that as number 2. How would I separate it? I would probably use coffee filters. There we go. because the sand is not soluble, right? So once again, we would be using filtration, right? And size again. But the solubility also a factor because it is insoluble in water. And the density is also a factor because it made it go down to the bottom. That should have been 4. I'm sorry. And this one would be 5, right? The last would be the salt because it's a little more complicated. Here we're going to use evaporation for, right? For the separate, how to separate. What are we going to use? We're going to use a lot of stuff. So you notice we're just talking. We haven't even explained how we're doing anything. This is just a quick thinking through it. Okay, we're probably going to use hot plates, watch glasses, beakers. So it's a lot of stuff to be used on this one. And the other one's the beaker. Because we got to catch it in something, right? Where's the beaker? Beaker. There it is. We actually need that one. Yeah, okay. I'm trying to read to see if there's anything else. No, that's it. Okay, so we're going to use the beakers also. Just one. All right. So solubility, yes, but also boiling point, right? Okay. So now we need to start talking about it. Number 1, we said we were going to use the sieves to filter out the copper BBs, right? That's it. Or to separate. I can say separate it out. It doesn't matter. 2, use and this is you're writing it so that if somebody was coming after you and you weren't there, they could follow your directions and do exactly what you did, okay? Use the magnet to separate the iron filings. Okay, there we go. All right. The next thing is add water so that the styrofoam will float. And will sink to the bottom. And the salt will dissolve, right? There. That's your, see, there's your additional step. Because you got to do that, otherwise this won't work. All right, number 4 would be to use the coffee filter. No, not yet. We haven't done that yet. Use the fish nets to retrieve the floating styrofoam pellets. Use the coffee filter, or you can just say pass the water, it doesn't matter. Remove the sand from the salt water. From the salt water, making sure to catch the salt water, what waster water in a beaker, right? Then 6, put the beaker containing salt water on the hot plate and cover it with the watch glass to prevent glass to prevent spattering. Well, actually, it'll still do the spattering, but it won't go outside, right? All right. All right. Boil ut. This is ut. This is supposed to be put. I was like, ut. Okay. Boil the mixture, right? Because that's what it is a mixture, until all the water has evaporated and only salt remains. That's how you would do it. You see? That would be my way of doing it. But the properties are not down here. If you put them up here, it's okay. You don't have to mention them down here. But if you don't put them in here, then you have to say use the sieves to filter out the copper BBs because of their size. Right? Use the magnet because you would have to say that because of its magnetic attraction. Like that, if you don't do that. And then here, because, and here you could say due to their densities, they're different densities. Let's put that. Densities. And the salt, oops. And the salt will dissolve due to its solubility. And here, densities and solubility here too, right? It gets more complicated if you do like that, but you can still do it, right? All right, and then so on and so forth. And then here you would have to mention because of its size, because of their size, here and then here too, right? Their size. So it kind of gets more tedious if you do it this way. I always look up there for the properties. And then here, and only the salt remains because its boiling point is lower than, it's higher, sorry. Boiling point is higher than that. See? So that's another way of doing it. Okay. So we put in most of the things we needed on here. So we put the sieve. See, this is what I do. When I look at the narrative, if this isn't here, if this is not done, then I will look for this. I'm looking for 3 things. Oops, I don't want to change that. I wanted to highlight it. Sorry. I wanted to highlight it. There we go. I'm looking for that. I'm looking what you did. You see that? And I'm looking for the property. So this would give you 3 points right there, right? I'm looking once again, magnet. That's there. Magnetic attraction. I'm not seeing something. I'm not seeing magnetism on here, but it's understood, right? The magnetic, oh, you could put it right here, look. There. then it would work right there. That would be 3, right? And then here, okay, this doesn't matter, but you are telling me that densities and solubility right here for those, right? And solubility for that one. And I'll keep these in mind as I'm grading. Okay, so you're using fishnets, and it's because of size. So there's another one right there. And you're retrieving. Okay, so you did not say, see this floating right here, or to filter out, but retrieve is good. I mean, you could, it's filtration. Okay, use the coffee filter. So once again, coffee filter I'm looking for. And because of their size right here. Okay, and that should have not been like this. That's cool. Okay. There. Remove the sand from the salt water. Okay. Put the beaker containers on the hot plate. So I'm looking for the rest of the stuff. Watch glass. And of course the beaker, what you needed. Otherwise the water won't be in there. Boil. See, there's the procedure. Boil, right? Until evaporates. There's another word that I'm looking for, because this boiling point is higher than that water. So boiling point, there's the property. You see that? So all of that was in there, except for one that I'm not seeing, and that would be the 2. You would actually have to say, instead of retrieve or remove, by filtration. You know, you could probably say retrieve through filtration, right? There. And then you would get that one too. Remove the sand by filtration. Again, right? So that would be the other one that I would have been looking for. Okay. So that would be how I would grade this. Remember that rubric? I would be applying it here. So you would have to give me each one, and you did do a narrative, so you would get your 5 there. You would get your 1, 2, 3 for that one. That's 1. So that's 1, 2, 3 for that one too. That's 2. So that's 6 points right there. This one is 1, 2, 3, right? 1, 2, 3 for that one. That's 9. That's 12 for that one. And then this one, you got all your stuff. You're boiling, you're evaporating, and boiling point. So you got 5. So you got all 6. So that's all 15 plus your 5. You would have gotten a 20 out of 20 with this one. You see? If you had incorporated, if you hadn't done this part, is what I'm saying. If you didn't do this part at all, right? This, only did this, then that's okay too, because this is just a planning stage. That's why I put it there, because it helps you write it. Once you start writing it, you see how I did it really fast, because it's all right here. So that's like your planning, your plan, your separation plan. Okay. So that pretty much does it for today, ladies and gentlemen. Or one lady and one gentleman. And that's it. We are done. Oh, just you, Karen. All right. Well, that's
That's
the,
just
okay. I didn't realize that Jabrea had left too. All right. Well, that was it. I'm going to stop recording here. Do you have any questions about last time? Hold on, let me stop recording.